In the depths of our solar system, Titan, Saturn's largest moon, stands as one of the most enigmatic and Earth-like worlds. This vast and alien moon, discovered in 1655 by Dutch astronomer Cassini-Huygens, has captivated scientists for centuries. But it was NASA's Cassini-Huygens mission that finally unveiled the striking details of Titan's unique environment. Covered in a thick orange haze, Titan's atmosphere holds secrets of a complex weather system dominated by methane, resulting in lakes, rivers, and even rain, mirroring Earth's hydrological cycle. Titan's frozen terrain, adorned with mountains, plains, and valleys, speaks of geological activity in unexpected ways, offering glimpses into a world both familiar and foreign. As humanity ponders the next steps in space exploration, Titan emerges as a strong contender for human and robotic exploration. Is it possible that this moon, shaped by alien lakes and unique weather patterns, could become humanity's next frontier? Could Titan hold insights into life's resilience, survival in harsh conditions, and perhaps even clues to origins of life itself? This deep dive explores the strange, icy, and utterly fascinating world of Titan, including its climate, geography, atmosphere, and potential for human exploration. In this journey, we reveal why Titan is unlike any other place in the solar system. NASA's Cassini spacecraft, huygens in 1997, reached Saturn's orbit in 2004 and became humanity's eyes in the Saturnian system. Cassini carried the Huygens probe, which after a 7-year journey was released to explore Titan. On January 14, 2005, Huygens entered Titan's atmosphere and successfully landed on its icy surface, making it the first and only landing on a body in the outer solar system. This historic mission provided an unprecedented look at Titan's surface, atmosphere, and weather. From Cassini's long-term orbital mission around Saturn, scientists gathered thousands of images and spectroscopic data, transforming Titan from a distant mystery into a richly detailed world. Through Cassini-Huygens, scientists found that Titan's atmosphere is primarily nitrogen, much like Earth's. However, the key difference is the presence of methane, which exists as a gas, liquid, and possibly even solid on Titan. With atmospheric pressure 1.5 times that of Earth's and temperatures averaging minus 290 degrees Fahrenheit, Titan is a world that resembles Earth's environment in structure, but not in temperature or composition. Titan's atmosphere, the only dense atmosphere in the solar system outside Earth, is composed of roughly 98% nitrogen, 1.6% methane, and traces of hydrogen. Layers of thick orange haze obscure Titan's surface, creating a visual and chemical barrier. This haze is primarily caused by photochemical reactions where sunlight breaks down methane, resulting in organic molecules that float in Titan's upper atmosphere and fall as an organic rain, slowly coating the surface. Titan's methane cycle is comparable to Earth's water cycle, but involves liquid methane and ethane rather than water. The cycle includes evaporation, condensation, cloud formation, and rainfall. Cassini observed clouds in Titan's atmosphere, and Huygens captured images of channels that resemble riverbeds, likely formed by liquid methane flowing down from highlands to lower plains and lake basins. In essence, Titan has weather, precipitation, and seasonal cycles, with clouds and storms occurring primarily near the poles during specific periods of its 29.5-year orbit around Saturn. Scientists believe that seasonal changes could increase methane rainfall, filling Titan's lakes and replenishing its river channels. Unlike Earth's rain, which is composed of water, Titan experiences showers of methane and ethane. This rain isn't frequent, but plays a significant role in shaping Titan's surface, contributing to erosion, creating river channels, and sustaining its lakes. This continuous process of precipitation, erosion, and drainage on Titan draws interesting parallels with Earth's geography, making it an even more compelling candidate for exploration. One of Titan's most astounding features is its vast hydrocarbon lakes, particularly near the poles, where liquid methane and ethane collect in depressions. These lakes, oceans, and rivers are the only known stable bodies of liquid on a surface beyond Earth. Kraken Mare, the largest known sea on Titan, spans roughly 1,000 kilometers. This vast hydrocarbon ocean holds more methane and ethane than Earth's oil and gas reserves combined. Cassini's radar identified smooth, mirror-like surfaces that revealed Kraken Mare's depth, suggesting it could be hundreds of meters deep, potentially even connecting with subsurface reservoirs. Alongside Kraken Mare are smaller but significant seas like Ligeia Mare and Punga Mare. These bodies of liquid hydrocarbons are surrounded by pebbled shorelines and gentle slopes. Ligeia Mare in particular is estimated to contain pure liquid methane, likely resulting from continual seasonal rainfall in the polar regions. These lakes and seas open a door to understanding hydrological processes outside the water cycle as we know it. Cassini identified river channels on Titan's surface, particularly near the North Pole. These rivers, fueled by methane rainfall, connect to larger lakes, feeding into delta systems much like rivers on Earth flow into oceans. Observations revealed river deltas and channels in Ligeia Mare, confirming that liquid on Titan flows similarly to terrestrial water bodies, following topography, converging at low points and forming lake basins. Chapter 4. Earth-like geography, mountains, plains, and pebble-strewn shores. Despite its vastly different climate and environment, Titan's geography holds astonishing similarities to Earth's. Titan's landscape includes mountains and hills that appear to be composed of water ice. Under Titan's freezing temperatures, water ice acts like solid rock, creating sturdy mountainous structures. The highest of these mountains, discovered through Cassini's radar, is approximately 10,000 feet or 3,000 meters tall, akin to the Rockies on Earth. Titan's equatorial region is covered with vast, dark plains and sand dunes. These dunes, formed from hydrocarbon particles precipitated from the atmosphere, are shaped by strong winds that occasionally sweep across the moon's surface. With patterns resembling Earth's deserts, Titan's dune fields indicate wind-driven surface processes that further shape this moon's topography. Upon landing, the Huygens probe captured images of rounded pebbles and rocks, which likely consist of solid water ice rather than silicate rock. These smoothed, rounded pebbles imply erosion caused by liquid movement, likely methane and ethane flows, over long periods. This discovery confirms that liquid interaction with Titan's surface is ongoing, reinforcing similarities between Titan's shorelines and riverbanks on Earth. Chapter 5. Could Titan support life? One of the most intriguing questions about Titan is its potential to support life. Despite its inhospitable cold and lack of water, Titan offers conditions that challenge conventional definitions of habitability. Astrobiologists have theorized that life on Titan, if it exists, might be based on methane rather than water. Just as terrestrial life depends on water, a different form of life could potentially utilize methane and ethane as solvents. Certain Earth extremophiles, like methanogens, microbes that produce methane as a metabolic byproduct, hint at potential survival mechanisms on Titan. Methane-based life would be unlike any life we know, relying on liquid hydrocarbons rather than water. While this remains speculative, Titan's methane seas and lakes, combined with organic molecules from atmospheric reactions, create an environment worth investigating. One of Cassini-Huygens' most significant discoveries was the detection of complex organic molecules in Titan's atmosphere. These molecules, including hydrocarbons and nitrogen-containing compounds, are potential precursors to amino acids, which are the building blocks of life. Titan's upper atmosphere contains compounds like acetylene, cyanide, and benzene, all essential in prebiotic chemistry. Chapter 6. Titan as a frontier for human exploration. As humanity's spacefaring ambitions grow, Titan emerges as a plausible frontier. Its Earth-like landscape and atmospheric density offer unique opportunities, but it also presents unprecedented challenges. The extreme cold, dense atmosphere and thick haze make Titan a challenging environment for robotic and human exploration. Operating in temperatures where water freezes into solid rock requires specialized equipment and materials. Furthermore, methane and ethane oceans may pose difficulties for traditional landers and rovers. as their liquid nature is vastly different from water. Despite the challenges, Titan offers unique advantages for exploration. Titan's dense atmosphere and low gravity provide ideal conditions for parachute landings and even powered flight. Titan's hydrocarbon resources could be used as fuel for in-situ power sources, and wind turbines could harness the moon's surface winds for additional energy. Titan's thick atmosphere provides radiation shielding, offering a safer environment compared to other solar system destinations. In 2027, NASA plans to launch the Dragonfly mission, a revolutionary rotorcraft lander designed to explore Titan's surface and atmosphere. Scheduled to arrive in the mid-2030s, Dragonfly represents the first mission of its kind, a multi-rotor drone capable of hopping from one location to another across Titan's diverse landscapes. Dragonfly will focus on studying Titan's chemistry, searching for organic compounds and prebiotic molecules, while analyzing the moon's atmospheric processes and geological features. Its scientific goals include studying surface composition. Dragonfly will examine organic-rich regions and analyze their chemical composition, looking for molecules that could be precursors to life. By observing and sampling Titan's lakes, river channels and dunes, Dragonfly will gather data to better understand the methane-based hydrological cycle. Dragonfly will assess Titan's potential habitability and look for indicators of biological activity, helping scientists evaluate the possibility of methane-based life. This mission represents a major step in Titan exploration, allowing us to witness its landscapes up close, study its chemistry in detail, and uncover potential evidence of life. Dragonfly's mobility enables it to access multiple sites, revealing different aspects of Titan's environment in a single mission, a capability that traditional landers lack. Chapter 7. Comparing Titan with Earth. Parallels and contrasts. Titan and Earth are strikingly similar in certain respects, despite their different chemical compositions and extreme environmental conditions. These similarities raise fascinating questions about planetary evolution and the potential for life. Earth-like processes on an alien world. Titan's methane cycle mirrors Earth's water cycle in a way that's unparalleled in the solar system. The cyclical precipitation, surface runoff, and lakes are analogous to Earth's rain, rivers, and seas, though based on methane instead of water. River channels, lakes, and dunes on Titan suggest that erosion, sediment deposition, and wind processes shape its surface, much like Earth. Although these processes occur at much colder temperatures, they resemble the patterns of Earth's geological activity. Fundamental differences. Titan's average surface temperature of -290 degrees Fahrenheit makes it a frozen world, even though liquid methane and ethane persist in these extreme conditions. Earth, by contrast, is warm enough for liquid water to exist. Titan's thick nitrogen-methane atmosphere is vastly different from Earth's nitrogen-oxygen environment. While both atmospheres can support weather cycles, Titan's atmospheric chemistry would be toxic to humans without specialized equipment. Titan's surface is rich in hydrocarbons, with seas, rivers, and even solid particles composed of methane and ethane. On Earth, hydrocarbons form fossil fuels, while on Titan they are a primary environmental element, creating an entirely unique ecosystem. These contrasts with Earth not only highlight Titan's alien nature, but also open new avenues for studying atmospheric chemistry, planetary geology, and potentially exotic forms of life. Chapter 8. Titan's potential as humanity's next frontier. As we look beyond Earth for possible habitats, Titan emerges as a scientifically intriguing, albeit challenging, candidate. The question is, could Titan become humanity's next frontier? Feasibility of human settlement. Establishing a human presence on Titan would require overcoming significant challenges, such as extreme cold and a lack of breathable air. However, Titan offers advantages that other bodies like Mars lack. Titan's thick atmosphere shields the surface from cosmic radiation, which could make it safer for long-term human habitation compared to unprotected environments like Mars. Titan's abundance of methane and ethane offers possible sources of fuel. These hydrocarbons could be harnessed to create energy for heating, electricity, and even propulsion, allowing potential colonists to rely on local resources. Possible habitation scenarios. Several imaginative concepts for human settlement on Titan have been proposed, including floating habitats, potentially powered by solar energy or nuclear reactors, could allow humans to live above the harsh surface. Submarines or underwater habitats designed to withstand liquid methane could allow scientists to explore Kraken Mare and other methane lakes in depth. Dome-like structures, pressurized and heated, could shield inhabitants from the cold, while methane-based fuel cells could power the base. The low gravity would make constructing large structures feasible, possibly supporting entire colonies in the future. Scientific and economic incentives. Exploring Titan's unique resources could provide knowledge and technology that extend beyond scientific curiosity. Titan may answer questions about the adaptability of life and conditions necessary for habitability. Discovering methane-based life would profoundly impact our understanding of biology. Titan's hydrocarbon-rich environment might offer a new frontier for mining, although its distance from Earth poses logistical challenges. As humanity progresses towards space resource utilization, Titan's hydrocarbons could be valuable in a future interplanetary economy. Developing technologies to survive Titan's environment would push the boundaries of human engineering and innovation, likely leading to breakthroughs in extreme environment survival, robotics, and habitat design. Chapter 9. Titan in the broader search for life beyond Earth. Titan's complex chemistry and Earth-like processes make it an essential target in the broader search for life. Whether life exists in Titan's methane lakes or even underground remains an open question, but Titan's environment expands our understanding of the types of worlds where life might be found. Titan's role in comparative planetology. Studying Titan enhances comparative planetology by providing a direct comparison to Earth's processes under vastly different conditions. Learning how these processes unfold on Titan will inform models of other icy moons and exoplanets that might have atmospheres, potentially supporting liquid environments beneath icy surfaces. Implications for exoplanet research. Discoveries on Titan may influence how scientists evaluate habitability on exoplanets. The conditions on Titan show that liquid methane could support atmospheric and surface interactions that might be stable over billions of years. Observing such conditions on Titan helps scientists assess how to look for biosignatures on exoplanets and better understand the diversity of possible habitats in the universe. Conclusion: Titan, an otherworldly destination with earthly echoes. In the strange, distant realm of Titan, methane rains fall from orange skies onto icy plains, flowing into lakes and seas that mimic Earth's oceans. This moon, Saturn's mysterious companion, is a place of paradoxes. It's both alien and familiar, resembling Earth in its landscapes and cycles, yet composed of substances and shaped by temperatures beyond our experience. Titan's intricate environment, with methane rivers and mountain peaks made of solid ice, beckons humanity to explore, investigate, and imagine. The Cassini-Huygens mission and the upcoming Dragonfly exploration have sparked a new era of Titan research, revealing a moon that may hold clues to life's adaptability and the resilience of planetary ecosystems. Titan challenges our definitions of habitability and pushes the limits of planetary science, serving as a natural laboratory to study chemical and geological processes unlike anything on Earth. Could Titan be humanity's next frontier? Perhaps. With its thick atmosphere, unique resources, and Earth-like geography, Titan is a world ripe for exploration, a place where robotic explorers and one day perhaps even human pioneers may uncover secrets that will deepen our understanding of life, geology, and the cosmos itself. As we stand on the brink of this new age of discovery, Titan remains a destination filled with mystique and promise, a strange yet tantalizingly familiar world that could expand humanity's horizons in unimaginable ways.